think this is going to be a short one. I want to talk a little bit about the direction of the induced EMF, or the direction of the current. Like we said, that the idea behind the minus sign in Faraday's law, minus n d phi dt, is that the induced current is in the opposite, creates a field that's in the opposite direction of the increasing field that created it, of the increasing flux. And that's called Lenz's law. And so we sort of just, that doesn't play a part in any calculation, but it does in the end tell us the direction of the current if we care about the direction of the current. There's some interesting demos that you can do in class, and it's kind of hard to do them on a video, but I do want to talk about one neat one. Let's say that you have a metallic tube of some sort. It's not magnetic, it's just made of metal, such as an aluminum tube. And if you were to take a magnet and you drop that magnet down that tube, so, and I can do this, I just haven't, I don't have the equipment with me to do a video, I wish I did, but if you drop a magnet down a tube, at any point in the tube, right, at any point, it sees an increasing magnetic field coming at it, right, because that magnet has a magnetic field around it. It's not a constant magnetic field. I'm just drawing one vector. It's got a magnetic field around it, and any point on the tube sees an increasing field coming at it. After the magnet passes, it sees a decreasing field going away, but let's just look at the points below the magnet. So the field, the flux is increasing in that direction, right? The flux is increasing in that direction. So it's going to induce a current around the tube, right? So we'll induce a current around the tube that is in a direction that opposes the magnetic field. So as that magnet, so if you drop a magnet in a tube, it'll induce currents around the tube. They may not be very large currents, so you're not going to electrocute yourself by doing this demonstration, but it does induce currents around the tube, and those currents will create magnetic fields which oppose the field that created it. So I'll just draw this one in here. Let's go ahead and green. So for instance, at that point in the tube, it's going to have a magnetic field pointing up. And that's going to be true for all the points. As the magnet approaches them, the magnetic field created is going to oppose the magnetic field coming at it. So what that ends up doing in practice is it slows down the descent of the magnet. It pushes back at the magnet and slows down the descent. And this is a really neat demo to see, is that as you drop a magnet through a tube, it drops slowly. If it's a metallic tube, that's non-magnetic. If it was magnetic, then the magnet would just stick to the side and it would never make it down. But if it's an aluminum tube, for example, it will fall. It will just fall slower than the acceleration due to gravity because of the induced currents around the tube as it approaches lower and lower points in the tube. That's Lenz's law, that the magnetic field induced opposes the magnetic field that created it. So I'm going to direct you to a video that shows this. It's not a terribly effective video, but it does show two magnets falling, one in a glass tube, one in a metal tube, and you'll see that one that falls in the glass tube falls faster than the one in the metal tube. So watch that video. It's only 30 seconds long.